with Daniel Jafferis. We'll talk about complex Chern-Simons theories and 5 branes on the squash 3 sphere.
Okay, well, thank you very much for inviting me to speak at the String Math Conference here. It's been a nice day so far. So I'm going to tell you about some joint work of mine with Clay Cordova, who's a postdoc at Harvard. And the idea is that if you take the 2-0 theory in 6 dimensions and put it in a certain way that preserves supersymmetry that I'll describe on a squash 3 sphere, you end up with complex Chern-Simons in the rest of the 3 dimensions, where the complex Chern-Simons coupling is related to this squashing parameter. So the main ingredient is that, so the reason why it's interesting is that you might take the 2-0 theory and twist it on some 3 manifold. And the 2-0 theory is labeled by some, it's not exactly a gauge group in 6 dimensions, but some AVE group, G, and you'll end up with some 3D n equals 2 theory labeled by the 3 manifold. That's been sort of analogous to the 4D Gaiotto theories. So this guy has only 4 supercharges, so in some sense they're richer. There are a lot more 3 manifolds than Riemann surfaces. And you may compute the partition function of this guy on the 3 sphere, which is a kind of nice quantity in 3 dimensions that characterizes 3D n equals 2 theories. And the idea here is that you can go the other way and relate this to some invariant of the 3 manifold. And along the way, I'm going to end up having to describe to you how to preserve supersymmetry. If you take maximally supersymmetric, so that is 16 supercharged Yang-Mills in 5 dimensions, and try to put it in some general background with lots of different kind of background fields turned on, so I'll explain why that's relevant. And at the end, something interesting will happen, where one will somehow trade supersymmetry for an emergent gauge symmetry and end up with complex Chern-Simons, which has a non-compact gauge group. So it's kind of naively unusual to get that from reduction of some supersymmetric gauge theory. So some of the 2 differences cancel. So that's the outline. So let me introduce the cast of characters. So first of all, complex Chern-Simons theory. It's just the complex version of ordinary Chern-Simons theory. So I have some connection for complex gauge group, which maybe could be SLNC, but it could be more general. And let me take the connection and write it in terms of a real part A and an imaginary part X. And then if I expand out the complex Chern-Simons action, it looks like this guy. So it has some part here, which looks kind of like ordinary Chern-Simons for A, and then this other more unusual thing. And a priori, the levels Q and Q tilde are 2 independent complex numbers. So it's 4 real parameters. And so Q and U might be, in principle, complex. It won't be on the next slide, but at this stage. And then it has non-compact gauge symmetry. So I have some GC valued scalar function, and I can shift the connection by the covariant derivative. So it's useful. Now, this thing is a little bit subtle to define non-perturbatively. So often in ordinary Chern-Simons with compact gauge groups, like SU and Chern-Simons, you would regulate the theory by adding 3D Yang-Mills terms, and that allows you to easily compute one-loop diagrams because you have an ordinary propagator. That doesn't work in complex Chern-Simons because the part of the gauge group, the complex part of the gauge group, the non-compact part, would have wrong assigned kinetic terms if you added the Yang-Mills term, so it doesn't really make sense as a regulator. So it's a little subtle to define the thing. The most ordinary version of complex Chern-Simons has the level K that appears here being integer for the same reason that it's quantized in ordinary Chern-Simons, so that e to the IS is invariant under large gauge transformations. And then if you take the guy U, the level U here to be real, then the whole partition function, the Euclidean partition function, is oscillatory, so it looks like it has sort of a chance to be well-defined. There's also another branch, if you take U to be pure imaginary, which would have corresponded to a unitary theory in 3 dimensions. Sometimes people consider more general choices like K not integer, or just U and K arbitrary complex numbers defined by some kind of alternative contour of integration in the space of fields, like written recently, but that won't make an appearance here. In this context, because this complex Chern-Simons is going to appear as a low energy limit of some construction that came from ordinary supersymmetric gauge theory, the original construction has completely well-defined path integral, and so in a sense it tells you in this particular context how you're supposed to define the theory non-perturbatively. It tells you what contour you should have used. It's the one that you got from the starting point. Okay, so of course the other ingredient here is the M5 brane theory, the 2-0 theory in 6 dimensions. So this has the biggest possible superconformal symmetry. So you can't have superconformal invariance above 6 dimensions, and this is the most symmetric one. And it's labeled by some ADE group, which is sort of like the number of M5 branes. And it has no marginal deformations, but it is believed to be a local conformal field theory, although it is intrinsically strongly coupled, and we don't know any Lagrangian for it. So that's in some ways why it's interesting, but also why it's hard. But the main property of this thing that I'll use today to sort of derive these results is that if you compactify it on a circle, then at long distances, much longer than the scale set by the compactification size, it looks like 5D maximally supersymmetric Yang-Mills. So I should say, some people use a funny convention in 5 dimensions where they call n equals 2 the minimal supersymmetric guy, but by n equals 2 I mean the guy with 16 supercharges, so twice the minimal one. So don't be confused by that. Okay, so with the gauge group G, that was the label of the 2-0 theory. So there's some conjectures that maybe you can just define the whole 6-dimensional theory from this 5D starting point. So maybe it's somehow non-perturbatively complete in some sense. I won't need that today. So first of all, in 5 dimensions, Yang-Mills is infrared free. So at long distances, Yang-Mills theory just becomes very, very weakly coupled. But at short distances, it's becomes strongly coupled. So in general, if I wrote down some 5D Yang-Mills theory, you wouldn't know how to make sense of it. It's non-renormalizable. But in this special, very supersymmetric case, it can be completed into this 6-dimensional theory. And in 5 dimensions, there are some kind of solitons that sort of look like a 4D instanton times time. And those are identified with the elliptic line modes of this guy on the circle. But really, what I'm going to talk about here, we're usually going to end up compactifying the 2-0 theory actually on a small circle. So it won't really matter whether on a big circle it actually looks like 5D Yang-Mills or not. And even more generally, when you compute some kind of supersymmetric quantities, like some supersymmetric partition function, then no one has shown it as far as I know, but it's very plausible that someone could show that all higher order operators that you might imagine adding to 5D Yang-Mills Lagrangian, some f to the 4th term and so, are probably all Q exact because you can write them as total superspace integrals. And that would mean that whatever is the exact 5D theory you get by putting the 2-0 theory on the circle, if you compute some supersymmetric partition function, out of it, you might as well just use the 5D Yang-Mills because the other things that you don't know won't change the answer anyway. But in this case, I don't even need that, I think. So, okay, so the theory I called TG of M3, the 3D theory labeled by a 3-manifold. What's the idea of it? These things were, I think, first introduced by Dimafta, Gayotto, and Gukov, but other people have also worked on them. So the idea is you take 3 of the dimensions out of the 6 to be wrapped up in some small 3-manifold. And if you want to preserve some supersymmetry, well, in this case, to preserve 4 supercharges, then you can take the normal directions to the 3-manifold to be in its cotangent bundle. So in other words, it's like I have in the 11-dimensional M theory R21 times this Calabi-Yau T star of M3 times R2, and this M3 is like a Lagrangian submanifold of this Calabi-Yau. So if I wrap my M5 brane on here and on the 3-manifold, it preserves some supersymmetry. So that's the case I'm interested in today. And if I do that and I work at long distances in R21, so this is some tiny 3-manifold, then in the infrared I'll flow typically to some non-trivial interacting superconformal theory. It might be for certain M3s, the theory is gapped, but not for hyperbolic three manifolds. And it's completely independent of the metric on the three manifold in this infrared limit. So unlike, say, in the case of compactifying the 2-0 theory on a Riemann surface to get a 4D gauge theory, where the complex moduli of the Riemann surface, you put it on, turn into marginal, some can turn into marginal parameters of the 4D SCFT. That doesn't happen in the 3D case, so you just get something unique. And at least for compact hyperbolic three manifolds, this theory has no flavor symmetries at all. So it's a very rigid thing. Okay, so just to elaborate in a little more detail, how does it work? Just to remind someone, so you wanted to preserve four supercharges, compactifying on an arbitrary three manifold, which has some arbitrary metric. So naively looks like it won't work because you want to find a covariantly constant spinner and you'll have some random spin connection. But what you do is you turn on a background R gauge field, so that's the twisting, so that at least for some of the spinners you can cancel this term with that term. And it's just kind of group theory. So you break up the original theory has an SO5 R symmetry. That's the R symmetry associated with 2-0 theory in 6 dimensions. And it has the full 60 rotational invariance, so that you break into the 3D rotations and the other 3D rotations, and you decompose the R symmetry in this way. That's a choice. And then you can, if under this decomposition, you see how do the spinners, the supersymmetries transform, they break up into this way. And so therefore, if I choose the diagonal of the SO3R and the SO3 Euclidean, then I'll end up with some supersymmetry that's like a scalar. So that's just saying that I cancel these two terms and I get a guy, just find a guy that's constant. So that's how one ends up with, in the end, 4 supercharges, which still carries this SO2R, which is a U1R symmetry, characteristic of 3D n equals 2 supersymmetry. Okay, so that's this theories we call like this. And they're interesting because they provide some different perspective on 3D superconformal theories. They might give you some examples that you couldn't write with Lagrangians, certainly can't easily write them with Lagrangians. In certain classes of examples of three manifolds, people such as these gentlemen have found abelian Chern-Simons matter theories that flow in the infrared to this theory. So sometimes they do have Lagrangian descriptions, and they use some tetrahedral decomposition of the three manifold. I won't talk about this much. This is all I was going to say about it, but it's hard for compact three manifolds. So there, I'm not even sure if it's supposed to work. In this talk, I'll mostly think about the compact case, but everything I say is probably, it was also true in general. Okay, so what am I going to compute out of this interesting 3D theory? How do I want to characterize it? So something that's become a very popular, useful tool to learn something about 3D conformal field theories is to compute the partition function on the sphere. Well, one reason is because it's kind of intrinsically defined. So on the round sphere, it's conformal to flat space. I can just map any CFT to it, compute the partition function at some infrared finite number that is just intrinsic to the CFT. That's true even if it wasn't supersymmetric, and it characterizes the number of degrees of freedom. So it's kind of the 3D analog of the anomaly coefficients in even dimensions, but it's much richer, like much more complicated functions. On the other hand, it's also nice because in supersymmetric theories, if you had a Lagrangian, then you can compute this thing using localization. And part of the reason why that works is that it's possible to preserve supersymmetry on the sphere even when you're not in a conformal field theory, and you get some supersymmetry algebra that, so the SU2 times SU2, which are the rotations of the S3, and this thing has 4 supercharges and an R charge. And then there's this interesting, and it's seemingly the only generalization, which is that you squash the sphere. So here it's going to be easiest to think about actually what's actually the squash sphere, which is I can think of the 3 sphere as a Hopf fibration. So it's like a circle fibred over an S2. And if I just change the size of the fiber relative to the base, that's the squashing. And of course, it preserves an SU2 times U1 out of the original SO4 isometry of the sphere. And it turns out, it's not obvious, it's not to me, but it turns out you can adjust various couplings, various sort of background couplings, which I'll elaborate more on later, so that you can preserve supersymmetry in this kind of background. For some reason, I think just by historical orders, this paper came first. It's been very popular to consider partition function on a different geometry. It's called the ellipsoid, also sometimes called the squash sphere, which is basically the solutions of this equation. So it's also some deformation of S3. Here Z1 and Z2 are complex parameters, so it's some different metric on the 3 sphere. And this guy only preserves a U1 times U1 isometry, so it's sort of more squashed than this in some sense. But it turns out that the supersymmetric partition functions of an n equals 2 theory in this space and that space are exactly the same if you identify the squashing parameters in this way. So L here is just the ratio of the size of the Hopf fiber to what it would have been in a round sphere. So that seems like these two things are completely equivalent, except for one caveat, which is important later, which is that the full range of the parameter here only covers part of the range here. So as you can see, this L is always less than 1 here, no matter what I do with B. So this ellipsoid corresponds, some ellipsoid corresponds to L less than 1 of the squash sphere, and L bigger than 1 than the squash sphere is just something different. But it's, of course, closely related. It's kind of analytic continuation. So I don't want to talk too much about this because it's not the main point of what I wanted to say today, but in general, in these supersymmetric theories, you can often compute the path integrals exactly using localization, and let me just remind you very schematically how it works. So in some Euclidean path integral, whenever I have invariance under supersymmetry, it means that if I compute the expectation value of the variation of any expression, it's 0 if the path integral was well defined. That's basically because it's like the integral of a total derivative. And in good situations, you can use it to show that the full path integral just is equal exactly to an integral over supersymmetric configurations with some one-loop determinant of fluctuations, but such that it's completely exact. So it's sort of like one-loop approximation is exact in this context. And the way it works is sort of simple. It just says that I take the partition function and I deform it by a different action with an arbitrary coefficient t. And of course, if I did it in general, the answer would depend on t. But if I take the derivative with respect to t, it pulls down this new action. And if I made the new action as the q variation of something, it has to be 0, so it's constant. So of course, I was interested in the theory without this extra thing. But if the answer doesn't depend on t, and this thing is positive, I could add it with a huge coefficient, and it just simplifies the calculation. And if you do that, it leads to formula like this for the partition function on the squash sphere of some kind of n equals 2 Chern-Simons theory coupled to matter multiplets with some R charges. I don't want to review this formula really, just showing it. And it involves this SB function, which is some interesting function, which has also appeared in, which also appears in Chern-Simons invariance. And I think that was what originally motivated this conjecture that that I'll say on the next page, so that's why I want to review this here. You get something like this. I mean, the origin of these things is, this is kind of the classical Chern-Simons invariant evaluated on the space of supersymmetric configurations, which simply consists of Coulomb branch moduli. And then there's a one-loop determinant from the vector multiplet and from the matter multiplets. So that's it. So in some ways, these conjectures are kind of surprising. So they said that the squash sphere partition function of that theory, Tg of M3, the 3D theory labeled by the 3 manifold, was given by some Chern-Simons partition function on the 3 manifold. That should be a subscript. And the funny thing is that it was not a supersymmetric theory on the three-manifold, and it has a non-compact gauge group. In a sense, it's very analogous to this AGT conjecture, where you would take the, say, S4 partition function of the theory you get by putting M5 branes on the Riemann surface, and it's related to some kind of total theory on the Riemann surface. So there's a similar flavor. It looks kind of mysterious. It has something to do with the fact that M5 branes don't have a Lagrangian, and it's some sort of mysterious system. But here I want to explain how you can actually understand it in a very sort of simple-minded way, just from some compactification of a supersymmetric gauge theory. But a priori, that sounds like, how could it work? Because I'll answer tonight it was something supersymmetric. How will I get this non-compact gauge symmetry? The precise conjectures here, I'm not saying it very precisely because there was something about them that wasn't quite right, but the general spirit is what we seem to find. I should mention there's something very analogous you could do if you computed what's called superconformal index, so not the partition function on S3, but on S2 times S1. And people made similar conjectures there, and there were some papers by Yagi and by Sang-Jae Lee and Masahiro Yamazaki that use similar ideas to what I'll talk about today to obtain a kind of similar answer. So we get complex Chern-Simons, in this case with the real part of the level being 0, and the other level being pure imaginary. Okay, so that's just a one-page aside. Okay, so how does it work in the S3 case? So the full, the idea is that, first of all, there's a full 60 background of the 3-sphere times the 3-manifold, which preserves 4 supersymmetries. So you could construct it completely in 6 dimensions. And then, of course, the partition function never depends on the overall scale of the whole 6-manifold, because the 60 theory is conformally invariant, and there are no anomalies because you have this 3-3 split of the geometry. And also, all the deformations of the metric on the 3-manifold are 2 exact, so the answer also doesn't depend on the ratio of sizes of the 2 guys. So therefore, you get the kind of picture like this. So I start here with this supersymmetric thing upstairs, and I may first reduce on the 3-manifold to get this complicated theory and compute this interesting partition function, and I get some number. Or I could try to just reduce the other way, just reduce it on this squashed sphere, and I'll get some theory on the 3-manifold, and they have to give the same answer because the partition function didn't depend on whether the 3-manifold was big or the S3 was big. But this step sounds hard because we don't know a Lagrangian for the 2-0 theory, so how do you can't just reduce it on a manifold. So the key point is you go through this intermediate step. We use this fact that on the circle, it looks like 5 Yang-Mills. And of course, the S3 has a circle. It looks like this kind of Hopf vibration. Of course, the circle is non-trivially fibered and so on. So it's not just the geometry. There's some kind of graviphoton turned on here and other background fields that you needed even in 6 dimensions to make it supersymmetric. But now you just have an ordinary supersymmetric gauge theory, and you can kind of turn the crank. So you reduce it on S2, you get something, and the answer must be that. And the point is that this something is going to just give you complex Chern-Simons. Right, so I sort of said this, you can't just directly reduce from 6 dimensions. After all, the whole reason why these theories you get by putting M5 brane on some manifold, the reason why it's interesting is because it doesn't have a Lagrangian. Otherwise, you just get trivial Lagrangian theories again. So I think, in general, anytime you have some setup like this, if you have some circle isometry, then you can proceed, and it's kind of algorithmic. So you reduce on the circle, you get 5 Yang-Mills in some background, and then you can just derive the answer. Okay, so of course, this reduction from S3 to S2, it's like Hopf vibration. So this psi is like the Hopf fiber variable. And of course, there's this off-diagonal term in the metric. So when you do dimensional reduction, it gives you the graviphoton, like background electromagnetic field that comes from dimensional reduction of metric. And there are other background fields. And if, of course, this 5-dimensional theory looks like a non-renormalizable theory with coupling dimensionful coupling equal to the radius of the Hopf circle. But that's not so much a problem here because we're actually interested in taking the three-sphere to be small. So we wanted the R to be small anyway, so that's the weakly coupled limit of the thing. So it looks simple. Now, in order to make it all work, you needed to find the complete six-dimensional background, which preserves supersymmetry, which involved, as I said, twisting on the three-manifold, but something else on the squash sphere, something more general. And then you reduce it to some five-dimensional background coupled to the dynamical Yang-Mills. And a general method, sort of advocated by these guys, of how to determine, how to write down extra couplings in some non-gravitational theory in a curved space so that you preserve supersymmetry is that you couple it to off-shell supergravity. And then you turn on the geometry you're interested in, and then you just tune the other background fields so that you end up preserving some rigid supersymmetry. And you can sort of imagine you take the limit en Planck to infinity. And it's important to have off-shell supergravity because you don't want gravity to be dynamical. It's just keeping track of certain terms that you could add to the dynamical theory, the Yang-Mills theory or the 2-0 theory in this context. So you don't impose any equation of motion on the supergravity fields or any reality condition, just whatever you want. Just keeping track of terms. The only thing you're interested in is whether the supersymmetry variation is zero. So it's a kind of machine to adjust the coupling so that it works. So that's sort of what I just said here. It turned out that, we couldn't seem to find how to do this for 5D maximal supergravity. It can be obtained by dimensional reduction of 6D off-shell conformal supergravity, and it kind of generalizes the 5D minimal supersymmetry case that had been done before. Oh, something happened a little bit to the table here. Sorry about that. But I don't want to get into these details in too much gory details, but of course in 6 dimensions you have the metric, you have the R symmetry gauge field, which is the SO5, and then you have some interesting self-dual 3 form and some kind of auxiliary scalar. And when you reduce to 5 dimensions, it gets messier. The metric gives you also a graviphoton and a dilaton. The R gauge field, the component along the direction you reduce on, gives you an R scalar. And this 3 form turns into some kind of 2 form. Because it's self-dual, you just get the 2 form. And it turns out in this example, all of these things actually had some role to play. I mean, I don't think you'll learn anything from this, but the supersymmetry variations are a little bit complicated, so these are the kind of things you have to check vanish to preserve supersymmetry. And it's like a big mess, but that's what it is. And then it's also possible to construct the 5D n equals 2 Yang-Mills action coupled to this general background. And mostly the background fields just contribute to masses, so it's a little bit boring, but there are some interesting pieces, like the graviphoton gives you this Chern-Simons term, so C is the potential. So this is like the usual Ramon Chern-Simons term on a D4 brane world volume. And then there's this interesting term which couples the scalars to the field strength and some new cubic coupling for the scalars. So these are sort of the 2 most interesting guys. Okay, now in the case of the round sphere, actually one didn't need to go through all this trouble because there's a simpler way to get there. So the H3, hyperbolic 3 space times S3 with equal radii is conformally flat. So I could have just conformally put the 2-0 theory there and then just twisted H3 to R3 and obtained the general theory in R3 upon reduction on the round sphere, and then that could just be put in the general 3 manifold. For the arbitrary squash case, it's more complicated, and all of these background fields get involved, this 2 form and this other scalar and so on, but it's all determined by just this one squashing parameter. Everything gets completely fixed by supersymmetry. So it looks a little bit messy, but it's not too terrible. And then you just turn the crank. So you want to reduce on the sphere. So in limit of the small sphere, it's basically only 0 modes that will survive. And the gauge field is pretty simple. You just get constants on the S2 with legs in the 3 manifold. The scalars just get zero modes. And of course, the fermions are a little bit more complicated. You don't have zero modes of the fermions on S2, but you pick up the lowest modes, which sort of transform in a doublet of the rotations of the S2. Yeah, so the fermion action isn't diagonalized in the mass basis, so you have to include some massive modes and integrate them out. It's kind of standard thing that could happen. So in the gauge sector, it's pretty simple. And the main interesting thing is that because you have this 1 unit of gravity photon flux, because of the fact that S3 is a Hopf vibration, you get this Chern-Simons at level 1. And of course, you get the reduction of the Yang-Mills term, but that disappears in the limit where the S3 is tiny and the 3 manifold is big, some irrelevant operator. And then the scalars also somewhat interesting. So it's natural to decompose them with respect to the breaking of the R symmetry. So there's 3 of them which get, in a sense, twisted to something like a 1 form, and then 2 which stay scalars. So these 3 I call X, these are Ys. And because of the coupling to some R gauge field, you end up with some 1 derivative kinetic term. It looks a lot like a Chern-Simons term. And then this interesting coupling of scalars to the field strength gives you this kind of guy. And this should also be familiar from that first slide when I showed you the expression for the complex Chern-Simons theory. And then the Ys give you something kind of boring. The fermions are more complicated, and I won't bore you with the details of it. But, and then there are also some non-abelian interaction terms, which again, fairly standard things for the most part. So how does it work? So the point is that if you change the contour of integration of these scalars, then it's natural to combine them together with the gauge field to make a complex connection. But at this point, there's only the ordinary gauge symmetry. There was no complex gauge symmetry. There's just some scalars. But the action looks almost invariant under the new gauge symmetry, which is the non-compact part of the GC gauge symmetry, except for one term, which looks like this. It's sort of, and this thing looks a lot like a gauge fixing term. So one starts to get suspicious. And if you fully integrate out the appropriate fermions to get the fermion action just in terms of the remaining massless ones, this thing B is just the epsilon and B are just some 2x2 matrices, the 0, 1, 0, and so on. Then you get some 2 derivative action. So that happened because the kinetic term for the fermions wasn't diagonalized in the basis of the massless mode. So the kinetic term mixed the massless guy with the massive one. So you integrate out the massive one, you convert the 1 derivative Dirac action to this funny 2 derivative action. So it looks like you get a ghost action for free. And then there's some also couplings to these X's. The Y business is kind of a nuisance, so I'll skip it. That's the technicality. And lo and behold, if you work out the Fadeev-Popov determinant that would have been associated with having gauge fixed the non-compact part of a putative complex gauge symmetry with that term, you find that it's exactly the fermionic determinant that you got with those lambdas. So it just fits together perfectly. So therefore, this partition function equals the partition function of the complex Chern-Simons with the real part of level 1 and the other level being this. And actually, interesting, both branches appear. So depending on whether L is bigger than 1 or less than 1, L equals 1 is the round sphere. This may be either real or imaginary. And one thing that's a little funny is that large L is obviously a kind of weak coupled Lippin. It's large Chern-Simons level. But that guy wasn't related to the ellipsoid where people were originally making these conjectures. So maybe B goes to 0. The sort of extreme ellipsoid geometry is related to small l, which looks not like a special value here. So maybe there's some kind of S-duality that can act on this partition function. And this is the last slide. So one thing which we're still working on is that once you have this 5D theory, it's straightforward to reduce it on the 3 manifold, and that will end up giving you some 2D, 2,2 gauge nonlinear signal model whose target is the moduli space of GC flat connections on the 3 manifold. And then it's put on the S2 in some way which depends on the Chern-Simons levels, and some superpotential that depends related to the Chern-Simons invariant, and it looks like it's just solvable using localization. So it seems like if you put it together, it will give you a formula for the partition function of complex Chern-Simons with arbitrary level on an arbitrary 3 manifold in terms of some kind of integral over the moduli space of flat connections. So, okay. I see that I ran out of time, so I should stop. Thank you. No, this is the last slide. So.
Questions?
Yeah.
Yes, there is some work by Kuda, Kawano, and Matsumiya on doing something with similar instability. They start from 5D super-young mills and reduce on 3 times S1, and they do the Fermion mills.
Right. Yeah, that is sort of related. That's true. So wait, so they remind me again. They reduce on. It's like S3 times S1.
That's right.
Okay, right, and they really reduce on the S1 piece. Like they reduce from 60 to 5D on the S1, and then yeah, okay, so it's some specialization of the 4D superconformal index. Yeah, okay, yeah, but it's of course similar spirit. I think of course one can do the full 4D superconformal index. It's just a little bit more work, but I mean once you start thinking in this point of view, it all looks algorithmic. So you just have to spend the work to find the 6D or 5D background, which actually preserves supersymmetry, and then, sometimes this could be kind of ugly.